This video lesson we're going to describe a process known as a Hohmann transfer, which provides a method that you can get a satellite into a geosynchronous orbit. So first let me point out an equation you should be familiar with, this one right here. If you're not familiar with this equation, go back and watch my previous video lesson on speed and distance at perigee and apogee. This is an equation that we can derive from two key principles: conservation of angular momentum and conservation of mechanical energy. Because it's arbitrary whether 1 means perigee and 2 means apogee or vice versa, the subscripts are sort of arbitrary. It means we can alternate them, and we can also write the equation in this form. Okay, so the Hohmann transfer. To get a satellite into a geosynchronous orbit, you can start by putting a satellite into a treetop orbit. So remember, that's a satellite that orbits at just a couple hundred miles of altitude above the Earth's surface. Now, how's that done? Let me zoom in. Typically, to put a satellite into a treetop orbit, a projectile is launched in what would be a parabolic trajectory if nothing was altered. Just give it an initial thrust from the surface of the Earth at some angle, travels well into the atmosphere, and comes back following this parabolic trajectory. When the object reaches the high point in that trajectory, if you provide the correct thrust or series of thrusts, then you can alter the velocity vector. And if it's tangent to the circular path with the correct velocity, then your satellite will maintain a circular orbit. And as we've derived in a previous lesson, that speed happens to be about 7,900 meters per second. That's the velocity of a treetop orbit. So as long as the satellite has that speed, then the pull of gravity toward the center of the Earth, combined with this tangential speed, corresponds to this uniform circular motion, and the magnitude of the velocity vector doesn't change, but the force of gravity just continually changes the direction of that velocity vector, and a circular orbit is maintained. So you can't just take a satellite, put it on board a rocket, and shoot it straight up so it travels to a distance of 6.6 times the radius of the Earth. You should recall that's the distance, or that's the radius of a geosynchronous satellite. You can't just shoot something straight up there and then when it gets there suddenly hang a sharp left or right and achieve a circular orbit. So the Hohmann transfer is the way to go. So let's say that vector represents a tangential velocity corresponding to an orbit that's practically equal to the radius of the Earth itself, thus a treetop orbit, and this is 7,900 meters per second. Now we can calculate what the velocity is, tangential speed, for the velocity, we'll call it v subscript g, for the speed of a geosynchronous satellite, is definitely a shorter vector than this velocity vector, because we know speed for a circular orbit is the square root of gm over r. So in other words, there's an inverse proportionality between speed and the radius of the orbit. In fact, if you use a calculator, we know what to plug in for g and m. For a geostationary or geosynchronous satellite, the value of r is about 6.6 times the Earth's radius, and the radius of the Earth is, as you know, 6.4 times 10 to the 6th meters. So given all these values, g is 6.67 times 10 to the negative 11th. The mass of the Earth is 6 times 10 to the 24th kilograms. If you plug everything in, I'll give you a moment. Yeah, you should find the speed for a geostationary satellite is about 3,072 meters per second. So how do we transition from orbit number 1 to orbit number 2? Well, as the satellite goes round and round along this treetop orbit, then when it reaches this point, if the velocity is increased, so it's something, well, we'll just say v greater than 7,900 meters per second, the result is an elliptical orbit, but not enough to send it as far away as a geostationary. So make this velocity even greater still. Then an even bigger elliptical orbit. Well, you see where we're going with this. If you can get the velocity to the correct value, then it'll go in an elliptical orbit, and its distance at apogee will be the same as this 6.6 times the radius of the Earth, which matches the orbital altitude for a geosynchronous satellite. Now also keep in mind, we know the velocity's got to be greater than 7,900 meters per second, but it also has to be less than 11.2 kilometers per second. Let's change this to 7.9 kilometers per second. You remember what this number represents, hopefully. That would be the square root of 2 times 7.9 kilometers per second. And once you increase the velocity of a circular orbit by more than 141%, or more than rad 2, then you've achieved escape velocity. This is starting to get messy, so we've got the same diagram drawn again here. So that's it. That's the idea of the Hohmann transfer. We want to change the velocity, suddenly give a thrust, increase this velocity from the treetop value of 7,900 meters per second up to a velocity, I'll just call it v subscript p, the p for perigee, because we know the result is going to be an elliptical orbit. And this distance is going to be the closest distance to the Earth in that elliptical orbit. So when the satellite travels around to this point, then by either the law of equal areas or law of conservation of angular momentum, the velocity here at apogee is going to be something a bit less. This black vector here, I don't know what it is, but we'll call that v subscript a for the speed at apogee. So let's see if we can figure out both those speeds based on this formula. Maybe we can draw this a little better. Here we go. Okay, so 7,900 meters per second, that's the speed of a treetop satellite of the Earth. Remind myself again, 3,072. That's the speed for a geosynchronous satellite. We need to find the speed at perigee for not this red track that represents a circular orbit, but for this purple track that represents the elliptical orbit. And there's another velocity we don't have in here. If everything is left alone, if you increase the speed from 7,900 meters per second to whatever this value happens to be, then as kinetic energy decreases and gravitational potential energy increases, it reaches this point at apogee, and the velocity vector has to be some smaller value, v subscript a. So these are the values we want to try to determine using this formula. Okay, well, we also need to know some distances, so let's see. And I guess we can call this distance right here r subscript p, but we know that value. That's basically the Earth radius of 6.4 times 10 to the 6 meters. And then we also need to know this distance, and we have that. That's 6.6 Earth radii, which is about 4.22 times 10 to the 7th meters. So those represent the values of R1 and R2 in this equation. So R1 is 6.4 times 10 to the 6th, and R2 is 4.22 times 10 to the 7th. So let's solve for this speed. So here V1 and what I'm calling VP, speed at perigee, are one and the same. So the speed at perigee has to be equal to the square root of 2 times 6.67 times 10 to the negative 11th times 6 times 10 to the 24th divided by 6.4 times 10 to the 6th times the quantity 1 plus. Now we can write this one of two ways. Well, this value of 4.22 times 10 to the 7th came by multiplying 6.6 times the radius of the Earth, but R1 is the radius of the Earth. So really we can say this is just 1 plus 1 over 6.6. Okay, time to grab your calculators. Give me a moment. A lot of numbers to plug in on this one. Almost there. There it is. We get the speed is equal to about 10,420 meters per second. Now notice something about that. Just like we suspected, that falls somewhere within the range, greater than 7,900, but less than 11,200. So this would be the speed of a treetop orbit, and this, of course, would be escape velocity. So that's a reasonable answer. So there, we can label that. This value is 10,420 meters per second. So that's step 2 of the Hohmann transfer. Step 1 of the Hohmann transfer is get a treetop orbit established. Step 2, at some point along that circular path, thrust and increase the speed to 10,420 meters per second. What will result is an elliptical orbit that sends the satellite out to a distance of 6.6 times the radius of the Earth. Now, if nothing was done at that point, sure, the velocity here is going to be less, but then the satellite's going to fall back in, and when it reaches this point, this speed will be back to 10,420, and it'll just continue on in this elliptical orbit, and that's not geosynchronous. So let's figure out what the speed would become at this position if no additional thrust was made. Well, this is easy. We don't actually have to apply this equation again, although we could. The easy way to do this one is just consider conservation of angular momentum. So m v1r1 equals m, v2 r2. We can cancel out the m. If we want, we can replace the subscripts. 1 represents perigee, and 2 represents apogee. Okay, so we're trying to find the speed at apogee now, so it should be the speed at perigee times r perigee over r apogee, but we know this value is 1 over 6.6, so the speed at apogee should be 10,420 meters per second times 1 over 6.6, which gives about 1,580 meters per second. Which, as you can see, is something less than 3,072 meters per second. So there's going to have to be another input of energy at this point. Step 1, Hohmann transfer, get a treetop orbit. Step 2, provide some thrust at any instant along that treetop orbit. It sends the satellite onto an elliptical path, and then to avoid having the satellite fall back in and complete the second half of that elliptical orbit, satellite starts on the circular orbit, receives this thrust, travels half of an elliptical orbit, and then before it starts to fall back in, you increase the speed from 1,580 meters per second up to 3,072 meters per second. And once that speed is achieved, then the final result of a circular geosynchronous orbit is satisfied. So there you have it. There are 4 different velocities that you can calculate for that describe the changes in speed for this maneuver known as a Hohmann transfer. Thanks for watching.